heat up a liquid, the molecules move faster, they go to the gaseous phase, they have more disorder. And when we talk about the next chapter, we're going to start talking about energies of gases, which is stuff like enthalpy and entropy. So we're looking at the disorder and calculating it. It's not good. The particles are further away, so they occupy spaces that are larger than a liquid or a gas. They don't always combine. They like to bounce off of each other and go in different directions. So in order for us to see a reaction, we have to have the right collision. And exactly what we base it off of is real gases versus ideal gas. So when we talk about the ideal gas law, we actually have a constant that we have to use to put our gases into ideal behavior. If not, they are going to act like real gases, which venture off of that ideal. And of course, following that gas behavior by using a kinetic model. Kinetic means movement or kinetic energy. Just looking at three states of matter again, we can see that the particles are further apart for a gas. So you have a solid, a liquid, and a gas, something like collecting on a vacuum line. The particles are close together when they're a solid, not a lot of movement around, very fixed position. They start to get a little looser in the liquid phase, and as a result, that's when we start to see more movement or the flowing of the liquid, depending how thick it is. And then, of course, the gas, they're so far apart that every once in a while we'll see a collision with them. And if the collisions are good, we get a product out of that. So it goes with the theory as if I were to open up a bottle of perfume on this side of the room, it would actually fill the space of the room, okay? Because the molecules will travel in that open space. So we have a large space there. All right, so we're going to talk a lot about pressure, temperature, volume, and the amount of the gas. So those are the types of things that we look at. And the gas laws that we're going to talk about the different behaviors when you combine those things, like pressures and volumes, or volumes and temperatures, or pressures and amounts, and so forth. So there's different types of conditions that we look at. And so we can talk about just the general properties of the gas. They flow freely, they have low density, okay? They usually can be in any proportion, that's percentages of the gas, okay? Atmospheric air is the most reasonable one, where you have 78% nitrogen and 21% oxygen. The rest is argon, water, and so is carbon dioxide. So those are fixed gases, but they have other ones in different proportions depending on the atmospheric pressure. And of course, when we have a temperature differential, we'll see things happen to the gas. So an increase in temperature will decrease the pressure, okay? But an increase in temperature will increase the volume. So we talk about direct and indirect proportions. We also talk about solubility of gases. They do not like heat. Gases will come out of solution or out of phase in the heat, and the different types of ways that it does that. And what the volume is. It's much greater than a solid or a liquid because of the particles moving so far apart. In physics, they talk about pressure, and so do we. So we're going to read pressures for you. So when you go ahead and do a lab in here, you're going to base it off of either atmospheric pressure or changing the pressure conditions. So we still go with the general formula for pressure, which is force per area. And we say surface area. We want to look at pressure as it is on the Earth. Physics, they usually do variations from that. If by chance we have an altitude like Colorado or high altitudes in space, we're going to see that atmospheric pressure be lower than what we're used to. And then, of course, below sea level, it is higher. So we see a change in the way we feel as we go from one elevation to another, just because our body regulates to that pressure at the time. We also say force is pretty much exerted on it. And force has to deal with gravity as well. So your pressure differences are going to be location dependent. the other day. And you saw that they were sucked down just by when the vacuum came on. It's the same principle when you have the vacuum on or off in any type of situation that you're in. And when the vacuum is off, everything is at equilibrium, as we call it. The pressure regulates to whatever in the container. So that could be, you know, what we see here. It could be an aerosol. It could be anything. Okay. Although we have to know with an aerosol what type of propellant we're using, what type of material we're using, and whether it is very, very flammable or not. Okay, so when you see labeled things that say contents under pressure, that means it's a non-flammable substance. If you say highly flammable, that would be like your brake cleaners and different things like that, highly flammable, and we have to note the pressure when a vacuum is on it and when a vacuum is off of it. I worked 3 years in an aerosol division, so I got to learn a lot about that, and I found out that Fix-A-Flat is definitely going to blow a hole in your windshield, and up your dashboard if you put it in your column there, in your steering column or anything like that. You put it in the dash area, if it gets really hot, it can blow a hole through it. That's how the pressure can be. And that's vapor pressure that we're going to talk about later. We had a car that came in with that situation that occurred. We told them to put the Fix-A-Flat in the wheelbase where it was a little cooler in the car. So he couldn't figure out why his windshield blew completely off, and we told him. It's like a bomb coming on. So anybody who knows to dispel an aerosol or anything under high pressure, you have to dispel the contents in it before you can dispose of it.
Okay, well,
So
was he
that's,
okay?
very common. Pardon?
Was he like okay?
Oh yeah, he was fine. It happened when he was like somewhere else. He just came back and found that it was exploded. Yes, it could have been a problem, definitely. But he couldn't figure out, because when we were working on the aerosols, we had to go to body shops and different things like that to visit. He couldn't figure out what happened, and we told him. Okay, so very interesting things with those types of materials. So when you put the vacuum on, we expect it to change the pressure conditions. Either it's going to expand or it's going to shrink. And usually with a vacuum, we see pulling of the force. That's what you saw when you saw the powders going through the funnel. You saw the filtrate collect into the funnel, and then you saw your material there on the weight paper. All right, a barometer. This is how traditionally we have measured pressure. We still do this in your lab. We have one in the back of your lab. It looks like a thermometer. It still has the toxic mercury in it, okay? And traditionally, a lot of your thermometers that you guys used over the years had mercury in it because it expanded with heat. They found out if it spills, mercury is toxic. So they changed all commercial thermometers to alcohol-based, but they never changed the weather barometer. And you'll see on a weather report all different types of conditions of your air, and one of them is the barometer reading. And usually in laboratory, one of us who's doing that will read this for you. And they'll just read the level of the mercury that comes up. We call this millimeters of mercury, which has pretty much a condition of 1 atmosphere. So when we go ahead and convert it to atmospheres, we have to know what the level of the mercury is. And we say the perfect idea is 1 atmosphere, 760 millimeters of mercury. So that would be our conversion. So if I went into your lab and I said, today our barometer reading is 750 millimeters of mercury, put it into atmospheres, you'd have to use that conversion factor, 760 millimeters of mercury to 1 atmosphere. So it would just be a way to do that. Then we have other types of systems, open and closed systems like vacuums, that are very similar to the barometer, only they collect gas in a vessel. Not necessarily do they see the mercury go up just based off of the temperature of the rooms in an open system. So in this case here, this would be more something that we'd see on a vacuum line. the manometer, and these are just general things that we have seen. Sometimes people have them as a way of showing a trick where they could actually pretty much pull the bulb with the heat of their hand and see the level go up, or reduce it and see the level go down. So depending on if you have a opened end or a closed end will determine if your pressure equalizes with atmosphere. So this is just another way to measure pressure, but if this is more in a closed system, releasing a vacuum or adding a vacuum to it. So the vessel that you guys used with the Erlenmeyer flask was considered more closer to an open manometer, but it's not, you know, this particular apparatus. It's just, it's similar to that. Common units of pressure. We stick with atmospheres most of the time, and you'll find that a lot of your gas laws that we're going to talk about have to be put into atmospheres. Okay, that's a very common thing. So at sea level, what we're saying, we live at 1 atmosphere, or a variation of that depending on if it's humid or if it's very cold. Millimeters of mercury is the way we can measure that by using like weather equipment. There's an old version of millimeters of mercury called torrs, and they are the exact same thing. So 1 atmosphere could be both of those, either millimeters of mercury or torrs. And we say those are the most common ways to measure our pressure. Then we have the older ways, which still exist, but one of them is pounds per square inch. That is all of your aerosols and all of your compressed gases. So when you go ahead and you see on the truck all these big old cylinders of gases, like, you know, argon, xenon, any of that stuff, they are measured in pounds per square inch. And so does a lot of aerosols as well. That is the contents under pressure calculation. And then the older ones, pascals and kilopascals, as well as bar. Bar is probably the rarest of them all. And you'll see that to 1 atmosphere, here is all of the conversion factors. So we'd say in 1 atmosphere, 14.7 pounds per square inch. In 1 atmosphere, 760 millimeters of mercury or 760 torrs, or something to that nature. So we definitely use these conversion factors all the time. So this would be a problem that we would do. We'd say, let's convert our units of pressure, okay? And this is just simple conversions as opposed to using a true gas law. And basically it's at room temperature, very important. We always have to say temperature conditions, or we're finding that. Now, in most of our calculations that we're going to do for the gas laws, that room temperature has to be converted to Kelvin. There are a few that have that acceptance, but normally Kelvin. And most of the time we don't have a manometer reading, but we could. So depending on the problem. So they're saying the closed-end manometer says I'm at equilibrium. The gas and the temperature are equal. And if I want to go ahead and use that value, how do I convert it to the different types of pressure readings I can have? How do I convert it to torrs? How do I convert it to atmospheres? And then maybe kilopascals or bars or pounds per square inch, whichever is being asked. So you use dimensional analysis just like you have for almost all calculations to do these conversions. So if we started out with 291 millimeters of mercury, one of the things they asked us for was, let's just go ahead and change that to torrs. Well, millimeters of mercury and torrs are the same thing. So in this case, you would just have a 1-to-1 ratio and you'd be done. It's just a matter of changing over the units. Now I could go to the second one and use that value that I have, and I could have done it in millimeters of mercury or in torrs, because the value of 760 is for both of them. So all I would do is divide the two together to get rid of the torrs, and that would be my atmospheres. And that is very low pressure compared to a 1 atmosphere. And I could always take any of my atmosphere calculations and use any of the other conversions that I want. The pounds per square inch, the pascals, the kilopascals, the bars, whatever. It's probably the easiest conversion because we're always saying 1 atmosphere of pressure at sea level will equal a certain amount. So we go ahead and use whatever the conversion factor is. Cross out what we don't want, accomplish what we do. So those are the different ways we can do pressure conversions. All right, so getting to the gas laws. A large portion of the gas laws, they have formulas. They're not that difficult to do because we're basically plugging in numbers and solving for an unknown. We're always using 2 sets, the initial conditions and the final conditions for almost all of them, with exception of the ideal gas law. We consider different properties, and then that's how we can approach the problem. We're going to look at pressure, and that's usually in atmospheres. Sometimes millimeters of mercury, but atmosphere is most popular. Temperature, most of the time, probably 99% of the time, it's in Kelvin. So we have to know how to convert to Kelvin. The volume interchanges between milliliters or liters, liters being preferable. So usually if we're doing molar volumes of gas, we would use milliliters, but if we're using the gas laws, we want to stick with liters. And then the amount is the number of moles, not grams, moles. So we have to be able to convert any gram quantity that we have by dividing it by its molar mass, okay? So N will signify the amount in moles, V will be volume, T will be temperature, P will be pressure. And then we have 2 universal gas constants that we will focus on in here. There are many more depending on the units of pressure you use. So if you use atmospheres, we have 1 set of gas constants that you guys will see in a few minutes. One is the universal gas constant, the other one is the energy gas constant. They're 2 separate things, and we will use them depending on the calculation we have. An ideal gas is what we'd like to bring all our gases into, okay? That's where the universal gas constant comes from, is being able to put it into ideal behavior to see what happens. But normally, real gases are going to be what we initially would look at if we did not set it into that ideal behavior. So we have a few calculations that show us what a real gas would look like. So we're going to look at different ones. We have different laws. And it's important, I'm going to write the actual formulas on the board for you, but it's always important to know what you're looking at, okay? So we have Boyle's law, we have Charles' law, we have Avogadro's law, we have Gay-Lussac's law, okay? We have the ideal gas law, we have Dalton's law of partial pressure, we have van der Waals law, we have the law of effusion. So these are all different types of laws that we can have. The first sets that we're going to talk about are going to be the simple ones that say, let's hold certain variables constant while we look at the behavior of the others, okay? So if it's not mentioned in the formula, it is considered to be constant and it is not going to be used, okay? So the first one is Boyle's, and this one is always going to be for a set of conditions that are initial versus final. And you could say I, initial, and F if you want. It doesn't matter. But that is what we would use. And this is Boyle's. And it's saying I am comparing my initial conditions with my final, or if I have final conditions, what did I start with? One of the 2. This is known to be indirect proportion, which means if I have an increase in pressure, I have a decrease in volume. If I have a decrease in pressure, I have an increase in volume. And if you see there, you have those nice direct proportional graphs that go with that. We concentration equation that we did in the previous chapter, if you set these equal to each other, you're dividing, when you find, let's say you want to get P1, you would multiply these two together and divide by the V1. Okay, so you're always going to be able to cancel out the units you don't want. So pressure and volume, and this is going to say that my temperature is constant and my amount in moles is constant. So I'm not going to concern myself with how much gas I have and how hot or cold it is. I don't have to worry about that. So that is boils, and that's what we have up here, where it's saying if I increase the volume, my pressure went down. If I decrease the volume, my pressure went up. And if we think of it in just the normal terms, if you push down on something and you're pushing a lot of pressure, it's getting smaller. So increasing the pressure, decreasing the volume. If you let it pop up, the volume has increased, the pressure has decreased. You have to think of it in terms of just regular, ordinary examples. So that would be boils. And how would we do that in the classroom is we would probably just measure some barometer readings, and we change the volume, and we would get like a data table like we have here, and we would be able to graph it, pressure versus the volume, and we would see that curve. So most of the time you're going to see a lot of slides that say PV is equal to a constant. Well, that's how we get each side of an equation. But what we want to do is we always want to use the law that I put right there, where we're comparing what happens if I change the conditions, okay? So this is a little bit confusing. A lot of people are like, well, isn't it supposed to be PV equals PV? Yes, that's true, but this is like one set of data, okay, without showing a change. So in general here it says, I'm only measuring pressure and volume. I do not care about the temperature or the amount of gas that I have. And of course, this is the indirect proportion. As one decreases, the other one increases, vice versa. All right, so that's Boyle's. Charles' law. Charles' law is going to deal with volume and temperature. It is going to hold pressure and the amount of gas constant. The difference is now we are going to divide instead of multiply. So the conditions are here holding the amount of gas constant and the pressure constant. So we are not going to focus on them. The temperature needs to be in Kelvin. So if you had most of your problems you're going to see on your problem set have them in degrees Celsius. So to review that, you would have temperature in Kelvin would be your degrees Celsius plus your 273. Now most of the time it's 273.15, but you can round it, it doesn't matter on that. So when you put your temperature into Kelvin, you can put it into your equation. Now this one, a little different. If I increase the volume, I also increase my temperature. And if you think about just general concept of that, if I'm boiling a liquid, the vapors are escaping to the atmosphere. It's a large volume. So I increased the temperature to get it to boil, and I increased the volume. And if I wanted to lower that temperature, of course I go to a solid state, it gets smaller. So if I decrease the temperature, I'm going to decrease the volume. So this is known as a direct proportion. And if you forget all this, anything multiplied set equal to itself is going to be indirect. Anything divided like this is going to be direct. Okay? So that is a trick that also to remember. Volumes can be in milliliters or liters, but if you're using this particular formula, make sure that every unit matches so you can cross them out. So if you have a milliliter and a liter, pick one to change it to. Okay, it doesn't matter which one you use. Liters are probably preferable, but it doesn't matter. Now, again, the same thing. I'm holding pressure constant. I'm holding the amount of gas constant. As one increases, the other one increases, and so forth. And my temperatures have to be in Kelvin, and they're directly proportional. We have another law that is very similar to the Charles law. This is known as Gay-Lussac's law, okay? And this one is only going to concern ourselves with pressure and temperature. So again, the volume is going to be constant, and the amount of gas is going to be constant. So this one is Charles. Okay? The next one down would be, we say Gay-Lussac's. And this one here is they're pretty much the same thing as Charles. It's a variation of Charles' law, but now we're just looking at pressure and temperature. Again, temperature must be in Kelvin. Pressures have to match their units. And as one increases, the other one increases, and vice versa. So these are three of our main laws that we have variations from. Now, when we're looking at the combined gas law, or we're looking at the ideal gas law, we can make changes and come into these laws, or we can derive the perfect world. So these are ones that are solely based on the derivation of an ideal gas eventually. So Charles, Gay-Lussac, Boyle's, most common ones that we look at. Then, along with that, these are saying I got three variables I'm solving for a fourth one. I always have one that I have to solve for. When I get to the next one, it's pretty much combining all of these, okay? Showing the changes using pressure, volume, and temperature, not being concerned with the amount, but having more to look at or to investigate. And that would be the combined gas law, and that is PVT is equal to PVT. And you can see here you got Boyle's law, you have Gay-Lussac's law, and you have Charles' law all in one. You're still going to expect that increase and decrease variables depending on what you're looking at. You're not going to be concerned with the amount of gas that is in there, because N is not mentioned, okay? And you see Boyle's law there, you see Charles' law there, you see Gay-Lussac's law. They're all there, okay? This particular one, you will have 5 numbers, and you're solving for the 6th one, okay? So all the rest of them, 3 numbers solving for the 4th, 5 numbers solving for the 6th. So we always have an unknown that we're looking at, and based on what our problem says or what our conditions are, we should be able to use any of these to solve any equation that we have that does not directly put it into ideal behavior. So we're just looking at general principles of just gases going on. The next one is Avogadro's law, and that is a very good variation of Charles' law. And here, finally, we're looking at the amount of gas that is around. So in general here, that would be V over N is equal to V over N. We're going to hold pressure and temperature constant here, and we're going to concern ourselves with the volume and the amount of gas that we have. And just like Gay-Lussac's and Charles' law, it's a direct proportion. If one increases, so does the other. And it is divided out, so again, we see that as Avogadro's because we're using the amount of moles, so that's why it's named that. Okay, and of course your volume should match milliliters or liters, and of course your n's have to be in moles, okay? So anything you see in grams, starting these problems has to be converted to moles, just like you did with mole ratios, molarity, molality, any of that stuff. So this is going to be Avogadro's law. So those are all the main common laws that we have, that a large portion of problem sets that come out of gas laws is giving you these conditions and solving for what they're asking for. Now, yes, you're going to see problems that make no sense at all in the atmosphere of the Earth, all right? Yes, it happens. They'll say, that's impossible. Yeah, it is, okay? But what gas law problem sets have come about over the years is people are just putting numbers in there. They're just putting random numbers in there. And yeah, it might make sense, it might not, but you're still seeing the trend. If you're working with Charles' law, you see an increase in volume, you see an increase in temperature, you're golden, okay? That's all you're doing. Don't think of the practicality of what really would happen on the face of the Earth, because most of the time these things don't make any sense when you solve them, just as long as you're seeing the trend. All right, before we start looking into problems, we also have to look at a concept called standard temperature and pressure. And the reason why this has to be noted is because this is the one that derives the ideal gas law. All of these conditions give you the universal gas constant if you were to do a math problem with it, okay? Because the universal gas constant involves the pressure, the volume, the amount, and the temperature all in one, and depending on what type of pressure you have. So in general, these are standard numbers. So when we're doing gas law problems, maybe I gave you a set of numbers, but I didn't give you another set to compare them to. Well, if I said at STP, that is the set of numbers that I'm using to compare it to. So you would know what numbers to have. So for pressure, it's always 1 atmosphere, standard. For volume, it's 22.4 liters. For moles, 1 mole. Okay? And what did I miss? Pressure, volume, moles, 1 mole, volume, yes. And temperature is always 273. Okay? So these are all standard conditions. And we're going to come up with a number when we do the ideal gas law that is called 0.0821. If you were to go ahead and put all these numbers into the right variation of that, it would come up to that number. So these are ideal sets of conditions that we can look at. So a common problem here would be like, use Boyle's law to figure out the volume when you start at STP. Well, you have a pressure and a volume on the one side, you're figuring out the other one on the other side. So you're using numbers that have already been standard. So the standard volume is always one thing, and of course we can convert if we have to. So what does that mean? That puts any gas into ideal behavior. Just like we're using Avogadro's number to always say that there's a set number of moles, molecules, ions, whatnot. So in general here, if by chance we're talking about helium, nitrogen, or oxygen, if we use these STP conditions, they're the same for all of them. The only thing that's different between the 3 gases is its mass and its density. So a question would be, oxygen and helium, what makes it different? It's definitely not STP, and it's definitely not the number of particles. Those are the same. It's only between the mass of the gas, how much space it occupies, and of course the density of it that we can calculate from the mass. So it has to be calculated from the mass. So these are why they're highlighted, is because these are the only 2 things that will separate the differences between the gases. But if you are using just the variables moles, pressure, temperature, and volume, there's no difference. the ideal gas law is exactly what I just said. If I use STP conditions, I am going to find the value that I need, okay? So it's a pressure and a volume. It's equal to a mole quantity and a temperature. What is R? R is a constant. R is a combination of all of that. And if you look at the units, you have the liters, the atmospheres, the moles, and the Kelvin. So you have all of the units. So when you're using the ideal gas law, you'd be able to cross everything out. But if you go ahead and take STP conditions, that is where that number derives from. So this is the very first universal gas constant we're going to use in here, mostly for behaviors of gases. If we're talking about energy of gases, we have another one that's separate from this, and that's towards the end of this lecture. So atmosphere is liters, moles Kelvin, you see the units, and it envelops anything at standard conditions. So we can use that to put a gas in ideal behavior, because we're not concerned about their grams, we're not concerned about their density, just ideal behavior. And of course, we could take the R value out and express all of R combined into one, where we have the pressure, the volume, the amount of moles, and the temperature, and if R was not existent, we could compare those to each other. So that's why it can tie into any gas law that we have. So when we look at that, how do we use it? If we have one set of conditions that we're looking for, we can say, oh, every time I see just one pressure, one volume, maybe one temperature, or something to that nature, in that case, we are going to go ahead and say, oh, I guess I'm going to use the ideal gas law. So then I set it into ideal behavior. And I could use any of my laws, like that combined one I had on the previous slide, to kind of get a derivation of this. So they're all related in some way. And it'll explain all of the different laws that we talked about by doing that. But it's just that universal gas constant that'll set it into ideal behavior, which in the real world does not occur. All right, so you guys are going to have a problem set. It's going to be related to gas laws, all right? First thing we got to do is we have to look and see what I'm trying to find. Because you got a lot of calculations, you got a lot of equations here, all right? And again, I would give these to you, but from just seeing the problem, can you pick out which gas law you are supposed to use? Okay? They have a volume here, and they have a pressure, okay? So most likely I'm already at Boyle's law, possibly, okay? Maybe I am at Gay-Lussac's, I don't know, but it's something that involves that, but there's no volume in Gay-Lussac's, so I can rule that out, okay? And then it says, what pressure, so that's my unknown, is required to compress the gas to this particular volume, okay? And this one says 1350 centimeters cubed. Centimeters cubed is the same thing as milliliters. So Boyle's law is what we're going to use. And we have to either convert the liters to milliliters or the milliliters to liters. We have to make sure that those units are converted when we do the problem. So we're trying to find the final pressure, or P2, as we call it. So we have an initial set of conditions, and we have a final set of conditions. So in this case here, we're using Boyle's law. We don't have to worry about temperature or the amount of gas. And before we even start, it says, go ahead and do this volume, and I have to I probably should convert the 1350 to liters, and I have to see if I'm increasing or decreasing just by looking at the change in volume. And that way, when I do the problem, I can check and see if I did the opposite with Boyle's law. So in general here, we have the 350 or the 3.5 liters. That's your one volume. you have the 925 torrs. It does not tell you in the problem to go ahead and convert it to atmospheres. You can use that pressure if you want, okay? It doesn't say anything else about that, so you can use it. Okay, so that is our one side. Those are our initial sets of conditions. And then, of course, P2 is what we're trying to find. That's our unknown. And, of course, we want to go ahead and use, saying that's milliliters, well, that would come out to be 1.35 liters, because that's milliliters. And all I did was, divide by 1,000. All right, so looking at my problem, before I even solve it, I have a decrease in volume. Okay, it went from the 3.5 liters to the 1.35 liters. So since I have a decrease in volume, I should have an increase in my overall pressure. All right, so that'll tell me that when I solve for the problem. And of course, all I have to do is divide it on the other side to solve for 2. All right, so when I do that, I use a follow roadmap, and I can say, okay, I'm going to use Boyle's law. I'm going to go ahead and set up my problem where I solve for the pressure, and I'm going to base it off of how I go and see if it decreases or increases. Now, in this particular case, they went ahead and just converted to atmospheres. Sometimes it's easier, but you do not have to do that. Okay, it's just easier for a lot of people to work in that particular realm. Like atmospheres are easier to work with, but you don't have to do that. You can use Boyle's law, and of course, you're going to see that my volume definitely decreased. So it went from 3.5, or 1.35 is the final value, 3.5 is the initial value. So my pressure should increase. So when I solved it, sure enough, my pressure has increased. Okay? And if I kept that in torrs, I would just have the value in torrs. I could have very easily did it that way as well. Because the problem did not tell me, go ahead and put it into atmosphere. But I think the standard practice is to do that. And of course, just solving for the problem is fairly easy after we have figured out which things to put into the equation and where. Okay, that's the first one. Everybody all right? Okay. And of course it says volume and pressure in this problem to start with. So that kind of gives you, oh, maybe I should use a formula that has that. The next one's saying, do volume and temperature. All right. So in this case here, I could go ahead and say, I could use Charles' law, or use pressure and temperature. I could use Gay-Lussac's law. And if by chance I have enough stuff going on, I might be able to use the combined gas law, depending on what is in the problem. In this case here, it looks like it's a Charles' law, gas law, because it has a volume and 2 temperatures. So I'm expecting, because my temperatures are increasing to 90 from 25, that when I do this problem, my volume will increase. Because again, you have a direct proportion. My volume's fine, I don't have to change it, but my temperatures I definitely do. So I'll take both of the temperatures and change them to Kelvin before I even put it into the problem. And then I set it up by just plugging the numbers in. Do not make it more complicated than it is. Pick the right gas law, do the correct conversions, and just plug the numbers in. That's as simple as it is, okay? Please don't overthink. That's a lot of people do that with these things. All right, so I have my initial volume, and I gotta convert them to K, all right? And then from there, I can figure out if my volume will increase because my temperature has increased. So when I solve, I definitely get an increase in volume, and it follows the laws that I have. So I took the 25 and I added the 273. I took the 90 and I added the 273. So I got my two temperatures. And V2 should not be marked as 1.95. Looks like a typo, so that would be what we're trying to find. So the 1.95 is the allotted volume I have. And it follows Charles' law, a volume to temperature relationship. If one goes up, the other one does, or vice versa. So as long as our temperatures are in Kelvin, we are fine. So that's what that one is. And you see, when we do an amount of gas, that would be a molar amount. So when it says the volume amount relationship, that means I'm relating volume of the gas to the amount of gas. I am not concerned with pressure. I am not concerned with temperature. And a large portion of your problems will say assume constant, and they will tell you which ones to hold constant. Here I am given two volumes and one mole value. So I'm looking for the other one. I am going to use a similar formula to Charles' law, which is this. So as my volume increases, my mole value should increase, or vice versa, okay? An indirect proportion. And of course, my volume should be of equal magnitude. And then of course, my moles will always come up as N. N is always moles, not grams. So when we look at this problem, we can write out what we know. We have 1 mole, 1.1 moles. We have 2 volumes. And when we see stuff like centimeters cubed, decimeters cubed, liters, micrometers cubed or something like that, you're going to go ahead and say that's a volume. There's probably a volume of a solid or something. So we could go ahead and just use that and not have to convert it to milliliters or liters because we can cross them out. Okay? But you can if you want. It's okay. It's just a little bit extra work. And we're expecting that our volume has increased. So let's hope our mole value increases if we are doing the problem correctly. So if we set that up, sure enough, as I increased my volume, I've increased my number of particles or moles in this case. And then, if by chance I have other things that the problem asked me, like in a reaction or something, if I found the moles of 1, I can figure out the rest of the problem as well. Very similar to the limiting reaction and the excess of that. So I should be able to figure out anything after I do that problem and have that information. All right. Now, those are just simple laws. Avogadro's law, we could do Gay-Lussac's law like that. We could do Charles' law, Boyle's law. And those are just looking at a few sets of conditions, maybe 3 variables you're solving for the 4th, and making sure that you always have your temperatures in Kelvin, your pressures have to equal each other, your volumes have to equal each other. So those are all different things that we look at. This one here is the combined gas law, because it's telling us to relate pressure, volume, and temperature, keeping the amount of gas constant. So in general here, we have pretty much 5 variables we're solving for, the 6th one. We're going to change our temperatures to Kelvin. We have 2 pressures that are at different units. One is in atmospheres, one is in millimeters of mercury. You'll end up with the same answer regardless. So we want to stay in atmospheres, that's the easiest one. However, if you did this in millimeters of mercury, you'd still end up with the same answer. So just pick one and follow that and make sure your pressures are even. And it looks like our volume that's final should be in liters. So here's all these numbers, and I have 5 of them. I'm going to use the combined gas law to solve for the variable that I need. So I look at my temperatures and I convert them. That's the first part of it. I want to go ahead and convert one of my pressures. And a large portion of the time, atmospheres is easier to work with. So we're going to just say, in that millimeters of mercury world, 1 atmosphere equals the 760. So we go ahead and we change it to atmospheres. Now our pressures are going to be able to be canceled out, and so are our temperatures. And after we solve the problem, we get a volume that fits all the conditions that match up, like increasing the temperature or increasing the volume. And we see that same direct proposition. In the pressure world, we decreased the pressure from 1 atmosphere. Does that fit the volume? And there's, so we can ask ourselves any of those questions, does everything make sense as far as just the calculation? So this is your combined gas law. That's combining Boyle, Charles, and Gay-Lussac's together. And you're just finding out which one you need to solve for. So this one here is isolating that variable that you need. And when you're doing gas laws, it's probably good to do what you see on the top here, arranging what numbers you have. So you have a V1, you're trying to find V2. So you know that. You have 2 temperatures. You read the problem, you say, which direction is that going? And then, of course, the 2 pressures. So if you list them, it's easier for you to pick the right gas law as well as calculate it correctly. All right. Now, this would be something where it's like I have an unknown gas, but I have some information that I need to know. All right. So this would be something like I have this volume, I have this amount, okay, and I need to know this pressure of this other one, okay? And it gives me my conditions, it gives me my temperatures, it gives me a mass, okay? It gives me a volume. And I have to first of all do my conversions and make sure that I have everything converted. And then I pick the right thing that I can use to do my gas law. So I'm going to convert my temperature to Kelvin, which is done there. My volume can stay in liters, no problem. And my amount is in kilograms. So the first thing I do is change that to grams, which is what we do here. And then I change it to moles by using the molar mass. Now, I only have one set of variables here. Probably not going to be able to do Boyle's, Charles, Gay-Lussac's, any of those. So what comes up? The ideal gas law. Okay? And I'm going to use the universal gas constant to do this as well. So my gas law is PV equals nRT. Okay? And we're trying to find pressure. So all we're going to do is move the volume to the denominator. So you're solving for your P. All right, so we have our amounts of gas. We have our R value. That is a constant, 0.0821. And it matches everything else in the problem. There are other types of gas constants out there, but it depends on what pressure you want. So if you want millimeters of mercury, you use a different number. And then, of course, the temperature. So when we plug everything in, we have set this particular unknown gas to ideal behavior because we're using the universal gas constant. We are able to cross everything out and get our value in atmospheres. Okay. Now I could have gone ahead very well and used a different gas constant, but whatever gas constant I use, I have to make sure I report the right number of pressure, either torrs, millimeters of mercury, or atmospheres. But we want to stick with the atmospheres as much as we can. Okay. Now, if we use something where we have to do a little bit more thinking, not just putting the problem up just doing the problem set and figuring out, oh, I gotta use Boyle's law, I gotta use Charles' law and stuff. I'm gonna be able to use a gas law, but maybe I have another question here. Does the proper equation fit? Okay, so is it one of these balanced equations? Can I say that they fit that particular mold by the conditions that I have? So I say here that constant pressure. All right, that's telling me that I'm not caring about pressure. I have a temperature, okay? And they're saying, assume the cylinder is isolated. Maybe this will be something that deals with the amount. Well, since I'm dealing with a balanced equation, chances are I'm looking at the end of what I'm looking for. So it's probably going to be using the Avogadro's law by just looking at that. So I'm holding pressure constant, and they say nothing about the volume. So Avogadro's law is ruled out because of the fact that I don't have the volume temperature going on. I thought there was a possibility because I saw the gas amount in there, but nothing is foolproof. We have to write it out. So we write the combined gas law including the amounts of gas. And that's exactly what we did. So we have the Boyle's law, the Charles law, the Gay-Lussac's law, and Avogadro's law all together. Okay? So that's what this top one is. Well, they didn't mention anything that I needed to know about volume, so I can rule that out. They didn't mention pressure. Okay? They just mentioned temperature and a balanced equation. And when we have a balanced equation, that's the amount of moles that balances it, the proper equation. So I cross out what I don't need, and I manipulate the equation the best that I can. I have the two temperatures, and I'm going to say, all right, if by chance I see it half or I see it increase, I can go ahead and figure out the amount that I have. So possibly 1 mole will be my second one, and my first one would be half. So depending on what I'm looking at in the relationship, I can pick the right equation. Now I'm not going to give you one of these. This is just showing that I have a balanced equation, and I can use a gas law to look at the answers that I want. Okay? It's not just saying, plug this number in and find this. Okay? Plug this number in and tell me the behavior. There are other ways we can use it. Okay? We can find density. We can find molar volumes. We can find molecular mass. There's other things we can do with it. And when they say 1/2, they're basically looking at the two reactants and the product. So we have to consider there's 2 moles here, 1 and 1, and only 1 here. So that's when they say it's a 1/2. And again, I am not going to ask you for that. It's just showing how we go ahead and manipulate an equation to get this particular answer that we want. So more than just solving for the unknown. All right, a couple more slides and we'll be done. Like I said, we can go ahead and find things besides balancing the equation. Okay? Or just solving for the actual ideal gas. We can go ahead and find other properties. And this goes into finding molar volumes of gas. In the lab that we do with this one is we pretty much put it under conditions where we trap the gas in a manometer that you saw, that bulb that you saw. And we start out with something very, very empty, and then as we boil and we increase the temperature, we collect gas in the actual bulb. And then the volume of the liquid moves into the actual glassware. And then we measure the volume, and then from there, we can determine changes in the atmosphere. So it's an actual experiment that we can do to find density or to find a molar volume, like a molar mass. So we know that it's mass over unit volume from density. So what does that mean? We can go ahead and say, if we calculate density related to moles, we can say molar mass over a mass and so forth. So if we put that into our equation for n, we can derive an equation for density using the gas law. So when we do that, we have a pressure, we have a molar mass, we have an R, and we have a T. So we are able to find density just by using the ideal gas law in front of us, and still using ideal behavior where we have the universal gas constant. And this is going to be the molar mass. This would be your pressure, your temperature, your R value. So when they cancel out, we get grams per milliliter, or maybe grams per liter, depending on what we start with. And we're going to say directly proportional to the pressure, just manipulating the ideal gas constant into this formula. So you don't have to do all the derivation here. This would be what you would be responsible for. The density is equal to this right here. Okay, so that's just showing the derivation of it. So I'm going to calculate a gas density. That is the problem that I want. And it looks as if I have, find the density of carbon dioxide. So this happens to be one gas that they want. They tell you what units to have it in. Not grams per milliliter now, it's grams per liter. And that kind of tells us right away that we are going to do a problem based off of the ideal gas law. So that's where it could come from. And they say as soon as you find your density, do one more step, find the molecules, which we can because we have a gram quantity. We can do that. So STP is the first thing they're talking about. So this is what we're talking about when we talk about different types of conditions that we can look at. They didn't give us any numbers. How am I supposed to solve the problem? You do have numbers. STP is a standard set of numbers that you can use. You can use the pressure, you can use the volume, you can use the moles, if you know them, okay? And then another one where I did give conditions, a pressure and a temperature, okay? Number one question I always get, when it's at STP, where are the other sets of numbers? I can't solve for it. You have that in front of you. So you're going to get the density, and you're going to be able to find this by using the numbers and properly putting them into the right equation. All right, so at 0 degrees C, that's the first one. They say, okay, change your temperature to Kelvin. We have to. They gave you an atmospheric pressure. They gave you a molar mass of carbon, well, they gave you the value that we have, which is carbon dioxide. So we find out the molar mass of carbon dioxide. And then it's just a matter of plugging it into the right equation for the density. So we have our pressure. We know what gas we're looking at, so we can just use the molar mass of that gas, the R value, and the temperature. And then, of course, we get our density from that. And because we are using the universal gas constant, we can cross out all units except for the grams and the liters. So we have them in the right units that we need. And then we have to go one step further because they just particularly asked for you to put it into molecules. So it kind of, incorporates what we've done before, where we have grams per liter, and we can just go ahead and use our molar mass and our Avogadro's number to find that. So molecules per liter. So using all these different concepts, and it builds on each other. So whatever they're asking, we have previous experience calculating that. All right. And then, of course, if we were to look at 20 degrees C, there's a difference here only because we raised the temperature. So we have to change that to Kelvin, but our equation is the same. The only difference is I changed the temperature. So instead of using STP, which was 273, I actually have a temperature here. And it was 20 degrees, so I go ahead and convert that. And I'm just pretty much solving it the exact same way. Finding the density, and then using that to get my molecules. All right. If we do molar mass, using the ideal gas law instead of density, we change it up just a little bit. We still have the R and the T. We still have the P and the V. Those are things that we look at. But now we have to convert our mole value to something just a tad bit differently using molar mass. turns out, when we derive the equation, we are going to use the mass of the substance that we have, like the gas, we're going to use, and then the values of what we collect with the gas. So this would be the experiment that I was telling you about, okay? We are going to weigh out the volume of that flask when we're done heating it. So that would give us M. We know we have this. We would record a temperature, and of course, I would give you the pressure of the room, and you would measure the volume in a graduated cylinder. So I can do grams per mole here by just doing that. And again, the universal gas constant will help me get that value that I need. So when I look at something like that, I have my values that I have in front of me. They said, I'm going to use petroleum as my fuel source that would vaporize, okay? I'm going to go ahead and say I have a certain volume of my flask. And in order for me to collect the necessary amount, I need to raise it to 100 degrees C, which would be 373 Kelvin. And I went and I read the pressure for you in the lab. So that particular day, millimeters of mercury or torrs is the same thing. It would be 754. And then the mass of the empty flask, which is what I started with, but then when I boiled everything, I collected a volume and I changed the mass. So it's just like you guys taking an empty flask and a full flask and taking the difference. So another way of determining mass or volume in some other system. So when we do that, we find out how much our actual gas is from the empty and the full, okay? So now we have a mass. That's part of our equation that we need. We have the R value, and we have a temperature, raising it 100. And then what we have to do is say, I'm going to use this particular universal gas constant. So my pressure is out of whack here. So I'm going to go ahead and change my pressure to atmospheres. Now if I wanted to use torr, I would use that gas constant, but I'm not doing that. And then of course the volume of what the flask was. So they gave us a 213 milliliter flask. I just changed it to liters. So now I have a molar mass. And then should I go ahead and look up what the molar mass of A4 gives me? It'll tell me what I have, what type of petroleum I have. All right, any questions? A lot more calculations, right? It's all about this in this class. All it is. I'm sorry. That's the way it is in the one thing that we should have